All right, so with three-phase transformers, there are three different configurations that we might see. Before we get into that, I want to just briefly explain that we can treat a three-phase transformer as simply three single-phase transformers connected together in some possible way. So the first one that I want to look at is a YY transformer. So in a YY transformer, that looks terrible. The primary windings are connected in a Y configuration, and the secondary windings are also connected in a Y configuration. So what we would see is something akin to this, okay? So I'm going to start on my primary side. So I'm going to call this terminal right here A1. Where this represents the A phase of the primary. So A is for the phase and the subscript is for 1 is for the primary. And I'm going to draw a section like this. So this is just my transmission line connection. And then I'm going to put an ideal transformer like so. I'm going to have dots on the same side. And then this is going to be my secondary. I'm assuming that my secondary is connected to a load, which is why I'm explicitly writing a capital A over here, because we use lowercase letters for the source side of the system and uppercase letters for the load side of the system. And this is going to have a subscript of 2 because this is on the secondary side as well. Okay. Now let's put something like this. So let's call this terminal right here lowercase b1. I'm going to put my dots on this side. So my dots are always going to be connected to my terminals explicitly. And trying to think about how to draw this the least horrifying way. So that guy is jumped over like that. So this guy over here will be C2. And then what I'm going to do is I'm going to take this guy across like so. So this will be lowercase c1. And I'm going to jump. Sorry, that jump did not look good. This guy over like so. And this is going to be B2. And then this is my neutral on the source side, and this is the neutral on the load side. like so. So this is just three coils on the primary side where the undotted terminal is tied together, and then three coils on the secondary side where once again the undotted terminals are tied together. So we can realistically just treat this as if it were three single phase transformers all connected together. Okay. So for a system like this, where let's say that there's N1 turns on all of the primary windings and N2 turns on all of the secondary windings, so that all of our coils are identical, what we would find is that, so let me define this as the magnitude of the line voltages on the primary. And bless you, this guy right here is going to be the magnitude of the line voltages on the secondary. This is going to be our primary line current. And this is going to be our secondary line current. So we could say for a system like this that the ratio of the primary line voltage to the secondary line voltage is the same thing as the ratio of the secondary line current over the primary line current is the same thing as N1 divided by N2, or simply A. And if we know our line voltages, then we can convert down to our phase voltages just by using that square root of 3 relationship and all of that kind of stuff like we learned when we were dealing with three-phase circuits. So all of those relationships still hold. Okay. The next one that I want to look at is our delta-delta transformer. So I'm going to try to set things up fairly similarly. This is going to be the A phase on the primary side. And let's make this guy down here the B phase on the primary side. Put the dot up here. Let's see here. That looks like shit. Okay. So there's one of our single phase transformers. I'm going to try to continue drawing some things here. So let me think. 1, 2, 3. So let's jump that over. Let's put the dot for this guy on the bottom like so. Here's my second coil. Here's my lines. And then dot. There's my lines. So I've got these three different triangular shapes here for my two deltas. So I've got my delta on my primary and my delta on my secondary. So let me just take this guy right here, jump it down like so. This is going to be C1. And now I'm going to start trying to draw my terminals for my secondary side. So this guy right here will be capital A2. This guy right here will be capital C2. Jump that over. And this guy right here will be capital B2. I'm going to define this voltage as the line voltages on my primary. This will be the magnitude of my line voltages on my secondary. This will be the magnitude of my line current on my primary. And this will be the magnitude of my line current on my secondary. And what we will have in this case is the exact same relationships that we actually had for our YY transformer. So we should see that the ratio of VL1 over VL2 is the same thing as the ratio of IL2 over IL1 is N1 over N2, or just A, the turns ratio of our transformers, where I'm going to, I guess, write N1 on this side and N2 on that side. Okay. And then we don't really have any phase voltages or anything like that to worry about in this particular system because there is no neutral to deal with, or we don't have any phase to neutral voltage or anything like that to deal with. So we would really just wind up working with these representations right here. Okay. The last one is our Y to delta transformer. Okay. So this is probably the easiest one to draw and probably the hardest one to actually figure out what the hell is going on. So I will do my best to make this work for you guys. So I'm going to put Y on top and delta on bottom. But obviously this could work in the opposite direction as well, okay? So I'm going to consider in this case my Y to be my primary and my delta to be my secondary. So what I'm going to start by doing here is I'm actually just going to put my transformers in first, okay? So let me start down here. And I'm going to put all of my dots on the left-hand side like so. And then put my double parallel lines indicating that we're dealing with ideal transformers. And then, so what I'm going to do is on the undotted terminal, I'm going to tie all of those together. At my neutral on my primary side like this. And now I'm just going to start taking make sure I give myself enough room here. Positive polarity terminals. So this is going to be lowercase c1. This is going to be lowercase b1. And this is going to be lowercase a1, like so. So I've got a Y-connected primary now, and now I've got to figure out how to get a delta-connected secondary. So to get my delta-connected secondary, I'm going to take my undotted terminal down here and my dotted terminal over here, and I'm actually going to tie those guys together, like so. And this will be my A phase for my secondary. Then I'm going to take my undotted terminal for this first transformer and my dotted terminal for this second transformer. And I'm going to tie those together, and I'm going to call this B2. And lastly, I'm going to take the remaining two terminals, which would be the undotted on my second transformer and the dotted on my third transformer, and I'm going to tie those together, and that will be my C2 terminal. And so what I should see is that I have one of my secondary windings between the A and the B phase, where the A is on the dot. I have another winding between the B and the C, where B is on the dot. And I have another winding between C and A, where C is on the dot. So for this particular system, what we would see is that when we're going from, oh, actually, let me define things really quickly here. So let's say that this voltage right here is VL1, and this voltage right here is the magnitude of VL2. This will be our current flowing in, IL1, and this will be our current flowing out, will be the magnitude of IL2, like so. And so what we should see is that when we do this particular configuration where Y is our primary and delta is our secondary, we'll get the magnitude of VL1 over the magnitude of VL2 is equal to the magnitude of IL2 over IL1 actually comes out to be the square root of 3 times our turns ratio. If we do it in the opposite direction, so if let's say we're counting our delta as our primary and our Y as our secondary, we'll have the relationship, the magnitude of VL1 over the magnitude of VL2 is equal to the magnitude of IL2 over the magnitude of IL1 is equal to A divided by the square root of 3. And again, if we have the delta connected as our primary, then we would replace those two subscripts with one subscript. And if our Y is our secondary, we would replace those one subscripts with a two subscript. Okay. So these are the three different permutations of three-phase transformers that you can have. And the Y delta transformer can be used in either direction. So you can have the Y connected to the primary or the delta connected to the primary. So now let's talk about tapped transformers. So let's say that on my primary side, I have a coil that has a total of N1 turns. And I'm going to put the dot on top here. And on my secondary side, my secondary coil is actually going to be split up into two different coils. Realistically, we could split it up into more than two coils if we were so inclined. But what I'm really trying to get out here is that our secondary consists of one whole coil, and then we make an electrical connection somewhere inside that coil. And so if I add these two guys together, essentially this is going to be treated like N2. And I'm going to call the number of turns for this guy up here NA, and the number of turns for this guy down here NB. Okay. So if I treat this as my primary current, I1, and this total voltage, let me do it out here, as V2, we would treat this exactly like we had a normal ideal transformer, okay? So what the taps are going to do is they are going to essentially give us access to two other voltages. So I'm going to call this guy right here VA, and this guy right here VB, like so, okay? So essentially we have the following relationships, okay? So we know that the ratio of V1 to V2 should be the same thing as I2 over I1 is our turns ratio N1 over N2 is equal to A, where there are, yeah, I've got it already listed, N1 turns, total turns on the primary side, and N2 total turns on the secondary side, okay? But we also know that V2, at least, is going to be equal to that voltage VA plus VB. And essentially, what we are doing is we are splitting that coil, and then the number of turns on each part of that secondary coil are going to tell us how that voltage splits. So if NA and NB were equal to each other, then VA and VB would be equal to each other because we're just literally taking that coil and cutting it in half and taking the voltage at that midpoint as kind of a reference, right? So realistically, what we would see is that, let me make sure I can math this out correctly. We could write this guy right here as VA would be NA over NA plus NB times V2, and VB would be lowercase b over NA plus NB times V2. So that when we add these guys together, we wind up getting NA plus NB over NA plus NB, which is just a factor of 1 times V2, so that V2 is equal to V2. Okay. So this is the type of transformer that's used in our homes, where we have what's called a center tapped transformer, meaning that we are splitting that 240 volts from the secondary side of our distribution transformer down into 2 instances of 120 volts, right? So that we have access to both 120 volts and 240 volts in our home, depending on if we're trying to plug in some small electrical appliance like, you know, a lamp or a television or something like that, or something larger like an oven, a hot water heater, and all of that kind of good stuff. We can use, so I've drawn an example here where we only have 2 taps, but we could have multiple taps. If any of you guys play electric guitar and you have an amplifier head, there's a multi-tapped transformer in that head that allows you to connect to a variety of different speaker cabinet combinations. Because some speakers have an impedance of 4 ohms, others have an impedance of 8 ohms, and others have an impedance of 16 ohms. And so you need to connect to the correct tap on that transformer in order to do the impedance matching to make your speaker cabinet look like the right size of load as compared to the output resistance of that amplifier. So these are things that are used practically all over the place, okay? Not only just in our homes, but they're used in all kinds of electronic circuits and all of that kind of good stuff too. Okay. All right, so the last ones that I want to talk about are our auto transformers, okay? So let's start with a step-up auto transformer. So auto transformers are a very specialized type of transformer because technically they only contain 1 coil, okay? So an auto transformer is going to kind of look like the secondary side of that tapped transformer that we just talked about, okay? So I'm going to draw a full system here. Okay. So let's say that I have some source voltage here, Vs. I've got some resistance here, R. And then down here, I'm going to have a coil that has N2 turns. And up here, I'm going to have a coil that has N1 turns, okay? And these 2 coils form essentially an ideal transformer. Now, I want to reiterate this. Realistically, this isn't 2 separate coils. It is 1 single coil that has been tapped, so that the total number of turns for this guy is literally just N1 plus N2, okay? And then over here, we're going to have connected some load impedance ZL, like so. So I'm going to define the voltage across this coil whose number of turns is labeled as N2. I'm actually going to call this voltage V1. So I'm considering this to be my primary voltage because it is on the source side of my system. And the current that is flowing into here is going to be my primary current, I1. And then I'm going to consider the voltage drop across my load, which is really just the voltage drop across both of those coils, to be my secondary voltage V2. And the current that's flowing into my load is going to be this current, I2, like so, okay? So it's going to require a little bit of math for us to figure things out here, but it's not going to be that much different than what we did when we were looking at the ideal transformer to begin with, okay? So the first thing that I want to remind you of is that our turns ratio, A for this case, is going to be essentially N1 over N2. Our mutual inductance between our coils is the square root of L1 times L2, which can also be expressed as A times L2. And our inductance L1 could be written as A squared times L2. And the derivation for where that definition for M and that definition for L1 came from was back when we were looking at an ideal transformer. Okay. So essentially what I can do here is I could solve for that voltage V1, okay? So I would have V1 is going to be equal to, so now I need to ask you guys a question here. What's the current that's flowing into the dot of the coil that has N2 turns? So I1 is the current flowing into right here, but then we have I2 flowing up like this. So I would argue from Kirchhoff's current law, that was not my intention. Let me redraw those things. Exactly right, Jude. Thank you. So the current that's flowing down here is going to be I1 minus I2. So what we will have is the impedance of that coil with N2 turns. So that's going to be J omega L2 times a total current of I1 minus I2. And then because our current I2 is flowing into the undotted terminal of that coil with N1 turns, we're going to have a minus sign on our mutual inductance term. And so that's going to look like J omega M times I2. And now we can substitute in that M is equal to A times L2. So we would say we have J omega L2 times I1 minus J omega L2 times I2 minus J omega A L2 times I2, like so. Are you guys okay with this algebra that I've done here? So all I've done is I split that first term up into its two constituent parts, and then I've substituted the fact that M, our mutual inductance, is equal to just A times L2. And so what I'm going to do now is I'm just going to try to kind of group things together, okay? So we can see that there is a common term of J omega L2 on all of these things. So I'm going to pull that out, okay? So I've got J omega L2. Then I'm going to have I1 by itself, okay? And then I'm going to have minus, and so now I have a so let's see, there's a whole I2 and there's a minus a I2. So let's do 1 minus a times I2, like so. Actually, that should be 1 plus a, my apologies. Because when I pull the minus sign out of both things, that's going to give me a plus sign in the middle there. We can write an expression for V2. There we go. Over here. Okay. So for this guy V2, actually, I'm going to do it down below because I want to make sure that I have enough room for it. My apologies here. So this voltage V2 is going to be the drop across coil N1, as well as the voltage drop across that coil N2 added together, since we're saying that V2 is that total voltage drop on the right-hand side, okay? So I'm essentially going to treat as if I have some voltage like so, positive polarity on the dot, negative polarity on the not dot. So my current I2 is flowing into the undotted terminal. So my self term for that coil N1 is going to look like minus J omega L1 times I2. Then my mutual term is going to have a plus sign here because we defined this positive polarity terminal at the dot. Okay, so that'll be plus J omega M. The current flowing into the dot of the coil that has N2 turns is once again I1 minus I2. And then lastly, we're going to add to that voltage V1. And now I'm going to expand all of this out, okay? So first thing I can do here is I'm going to have, wherever I see L1, I can replace it with A squared L2. So that's going to look like minus J omega A squared L2 I2. Then I'm going to have plus J omega, wherever I have an A, excuse me, wherever I have an M, I can replace that with an A L2 times I1, and then I'll have minus J omega A L2 I2, like so. And now I'm just going to substitute in that V1. So that was J omega L2 times a factor of I1 minus 1 plus A times I2, like so. And now I need to clean some things up, okay? So there is a common factor of J omega A L2 in all of these terms on the left-hand side. So I'm going to pull out that j omega a L2. Then I'm going to have an I1 like so. And so let me just make a note here. So I've taken care of this term, right? Here's where I have j omega a L2 times I1. Now, this guy right here is just an I2, and this guy over here is going to look like A times I2. So I'm going to have minus, once again, 1 plus A times I2. And now I'm going to add that V1 term. So I'll have j omega L2 multiplied by I1 minus 1 plus A I2. And we can see that both of these terms are incredibly similar to each other, right? So I have this term right here, and then that's the exact same term, except that there's another factor of A on there. So what I can do is actually simplify this down to look like j omega L2 times a factor of 1 plus A multiplied by that I1 minus 1 plus A I2 term. So expressing things in this way, what I can find is that V2, actually let me do it as V1 over V2, comes out to be j omega L2 times I1 minus 1 plus A times I2, all divided by j omega L2 times 1 plus A times I1 minus 1 plus A I2, like so. And the j omega 2 cancels the j omega 2. The 1 minus A plus that bit cancels this bit. And I'm just left with 1 over 1 plus A. I actually want to expand this out a little bit. Okay. So that is the same as 1 over 1 plus N1 over N2. So if I multiply this thing by a factor of N2 over N2, I wind up getting N2 divided by N1 plus N2. So this is how our voltages are related in this step up transformer. Okay. And this is going to be the same thing as the ratio of our current I2 to I1 based on a simple power analysis. So now let's talk about a step down auto transformer. So I'm going to draw a picture here, and I'm going to put my primary essentially where my load voltage, or excuse me, my source voltage where my load was in the previous example. So this is going to be Vs. Here's some resistance R. And then I've got a coil up here on top that I'm going to say has N1 turns dot on the top. And here's my coil having N2 turns. Actually, let me move those guys over here. And these guys are represent an ideal transformer. And once again, realistically, this is all just one large coil having N1 plus N2 turns, and it's just tapped somewhere in the center. And then our load is going to be connected over here. Where this voltage is our secondary voltage. This voltage across both of the coils together is our primary voltage. This is our primary current. And this is our secondary current. So we could suffer through all of that math again, or we could think about this for 2 seconds. So how do you think this guy is going to behave? Literally the exact opposite of the example that we just worked, because we're just replacing V1 with V2 and vice versa. So without doing literally any math whatsoever, and just thinking about it, we could say, that, goodness, V1 over V2 is going to wind up looking like N1 plus N2 over N2. Let me make sure that is indeed the opposite of what we have there. And that is going to be the same thing as the ratio of I2 over I1 for this guy. Okay. So the last thing that I want to talk about is just where we might see auto transformers. Okay. So auto transformers are actually pretty common. One of the reasons why they're so common is because they are significantly cheaper than a regular 2-winding transformer. Because since we only have one winding, we only have to provide enough copper to make one winding, right? So it is always cheaper to have an auto transformer than it is a traditional 2-winding transformer because it costs less money to produce it. An auto transformer also happens to be more efficient. So it will operate at a higher efficiency than a traditional transformer because you're going to lose less energy because you're only having to energize one coil, okay? That being said, the applications where auto transformers can be used are only in situations where our turns ratio is effectively less than 2. So we can't step down, let's say 13.8 kV like we have on the distribution lines here in Ruston down to 240 volts with an auto transformer. It's not meant for that kind of thing. But we could definitely step, let's say, like 495 kV down to 250 kV or something like that as part of a larger distribution network. Another thing that we need to take into account when we're dealing with auto transformers is that there is no isolation between the primary side and the secondary side. So what I mean by that specifically is in a traditional 2-winding transformer, the primary side and the secondary side are not physically connected together, or not physically electrically connected together, right? So we are using only induced voltages and currents to transfer energy from the left-hand side of the circuit to the right-hand circuit side of the circuit and vice versa. When we have an auto transformer like this that is composed of only one, there is no way to isolate the primary from the secondary because we have both a physical and electrical connection between those 2 windings because it's really the same winding, okay? So you'll see auto transformers a whole heck of a lot in the transmission side of electrical power distribution systems just because you usually don't have huge amounts of stepping up or stepping down voltages in those particular areas. You'll also see it where you need a good level of voltage regulation or efficiency as well, because they are inherently more efficient than a conventional two-winding transformer.